Hey, hi everyone. We are now going to look into the individual construct details. So today we will cover SystemVerilog interface. Let's jump into it. So the agenda that we want to address today is we will first understand what problem is the interface construct of SystemVerilog trying to solve, and then we'll do a brief introduction about it, and then we'll look into how to define an interface and how do we use it, for either for monitoring or for driving or for covering. How do we, or for the properties, how do we use the interfaces and how do we connect interfaces. So we look into connecting interface to testbench or connecting interface between two modules if you are doing a SystemVerilog based RTL design. Then we will cover what is the Modport and what does it do, and then interface as containers, wherein we will look at. So as we have been discussing, interface is equivalent to a module, SystemVerilog module. So we can put different type of other constructs that are related to solving the problem into the interface itself. Right, like we can put task functions, assertions, functional coverage. So we can put bunch of things into this. So how can we put it and what are some of the practical use cases for it? We'll look at it, and then how to design parameterized interfaces, which makes the interface more usable. How to do that, we'll look into it, and then finally we'll touch base upon the virtual interfaces, which is a bridge between your static world of signals to the dynamic world of class. So, and we'll conclude this session. So I want to just quickly refresh and connect back to the FIFO test bench that we had done. So this is the our FIFO test bench top, which we had looked at it. Or here we had created this instance of a FIFO interface, if you remember, and we had passed this clock and reset as input, and then we had done the assignments to the inputs of the interface for the reset and clock, and for the rest of them we had connected to the DUT. And then this particular interface we had passed it to the our program block, which was a container for all our test bench code. And within the program block we had environment and we had various test bench components. And what we had done was, to the environment we had passed it as a virtual interface, and to the different test bench components, for example to the push driver we had passed the push mod port, push interface mod port. To the pop driver we had passed pop interface mod port, and to the monitor we had passed the monitor mod port based virtual interfaces, right? So this is what we had seen as a part of usage. So we have to always remember how things get used, and then based on that context we should try to understand what the construct is. So now that we have looked at the use case of it, what we will now do is we'll go and deeply dissect this particular construct and understand it further. So first let's start with what problem are we trying to solve, right? So I am taking one example of APB master and APB slave. APB is a very popular protocol that's used in the SOC. So in SOC typically there are two types of buses that get utilized. One type of bus that's used internally within your chip for connecting different blocks, and another type of bus that is comes out of your SOC as a pins and connects to different peripherals. For example, USB is an external bus, PCIe is an external bus, whereas APB is an internal bus, right? So, and the way the place where this comes into picture is that you have a USB block, and then USB block will have an APB interface through which it will interface to your CPU, right? So there will of course be some sort of a network on chip, and to that network on chip will have a APB bridge, and your host will talk to the bridge. Host means CPU will talk to the bridge, and then the bridge will connect to different peripheral devices or the controllers, right? And then those controllers will expose the pins from SOC, and that will go out to the external world. That's how the overall thing works. But this is the APB is the internal connection between the bridge So in the bridges, typically you'll have a ASB master that can handle multiple slaves. Here I'm just showing a single slave. So what we have is we have a APB master and APB slave. Although I'm talking about APB, the concept of interface has nothing like specifically tied to APB, right? We are just taking an example that fits in, right? But the interface concept can be applied to any protocol or any set of interface signals. It's common, right? Okay, so let's coming back to the APB. So we have this clock and reset, which is common, right? And it's the input to both the master and slave, and the remaining signals, right? Like most of them are originating from master. For example, your P address is originating from master and going to the slave. P select is going to slave, enable is going to slave, write is going to slave, write data is going to slave, then the strobe is going to slave, whereas the read data is the only thing that is coming from the slave to the master, and then slave error is another thing that's coming from the slave to the master, right? So if we look at as an overall system, we have a set of common signals, and then the rest of the signals which are generally output from one side and input to the other side, or like here also similar, where the output from the slave side and the input to the master, right? So what this means from a verification standpoint, or is that what we require is we need to have the ability to drive some signals, and we need to have ability to monitor some of these signals, and we need to have ability to, like, whatever we are, like, either we are doing the checking or we are doing the coverage, right, on these signals, right? So that is the type of activity that will happen from a verification point of view on this set of signals, right? And the interface construct is is targeting to encapsulate this communication, right? And that is what is the problem that interface construct is trying to solve. Let's close on the problem statement now. So as we saw in the previous slide, right, we had a APB master, if we had a APB slave, and we were connecting them together, right? So now in this overall scheme of things, if we dissect it further, what exactly we are doing is we have some level of ports that are available to the APB master, correct? Like if the APB master were to be a module, then these will be the ports that will be available on the APB master, and these on the right hand side will be the ports that would be available on the APB slave design, right? So let's say P clock, P reset N would be inputs on both the modules, whereas P address will be output from the APB master module, whereas it will be input to the APB slave module. And then if I were to hook them up at some top, what I would have done is I would have declared wires and connected these ports between APB master and APB slave the way I had shown it in the previous slide. Now what this interface construct is trying to do is trying to encapsulate the ports of your DUT, the connection between these two ports, right? Both of them it's trying to encapsulate, right? So that's what we are showing it with this particular picture, right? So in this picture, what I am saying is there is a view to the, like, I am starting off, the way I am starting off the interface declaration is through set of signals that connect these two entities, right? How I connect master and slave is how I am starting to model the interface through set of your edge and wires, right? So bunch of wires or bunch of variables is how I start modeling, right? That's the starting point. But I also want to solve the problem of how these entities who are getting connected with each other view this particular set of interface signals. So the way we need to think about it is, generally when we start thinking about any signals, we start thinking about it from the point of view of a particular module, right? And then we look at a particular signal, whether it is an input or output. So in the context of interface, we are starting to look at it from the point of view of how these signals of one particular port get connected with another entity, right? Because ultimately it has to connect somewhere, right? So we start off from that point of view, the place where they get connected, and then from that point we view at both the entities which get connected. That's the difference in the perspective, right? So now if I do that, I have this interface where I have a bunch of wires, and then I have a view of these wires from a master side, right? What that view means is I would have just declared the P address as a logic, and then from the master's point of view, that logic P address would be viewed as an output, right? And from the slave side, that logic P address that I had declared over here would be viewed as an output, right? Sorry, the input, right? So that is how it will be viewed, and these views is what I am marking it over here. And along with that, now what we can do is we can also put any like a tasks or functions to drive these interfaces, or we can put checks to make sure the protocol that happens on these interface can be covered, and then any functional coverage that we want can be put together. So in overall, right, so what we did was the ports, the wires that we connect on in the top, and as well as the port on the other side, right, everything got contained within your interface, right? And along with that, since the whole interconnection mechanism is present, we are also able to put any driving, monitoring, checking, functional coverage if we want. The interface as a construct is capable of supporting it. So that is what is interface. Hey, now that we have understood what problem the interface is trying to solve, right, and we understood that it was trying to encapsulate communication, and we looked little bit further into depth as to what that communication is, right? So that communication is the ports of that particular, like the two connecting entities, the ports on two connecting entities, and the wires connecting them, right? That's the whole communication, right? So that's what the interface is trying to encapsulate. This is very important. Our view starts from the wires connecting them, but it also addresses the ports on both the ends that are getting connected, right? So the whole communication is getting encapsulated as a part of interface, and since everything is present at one place, all the verification related activities, right, which is like, you know, we are driving something or we are monitoring something for the purpose of checking or coverage, can all be put into the same construct. As an interface as a construct allows you to use tasks or functions, properties, coverage, everything you can put into it, right? Now why we should do this, right, and what is the benefit of doing it, that is what we will understand now. So when you use it as a design, when you use an interface, and then the view of an interface, which we call it as a Modport, as you had seen in the earlier example of the FIFO example, like a push interface and pop interfaces. So it makes it as a single entity, right? And then instead of defining bunch of wires, now you are defining a single entity, and then you connect that to another entity, right? And what that helps you do is that if at all this particular interface changes, if you add any additional signals, then you don't need to go and change it at multiple places, right? So you just change it at one single place, and then it reflects everywhere. So that's a benefit that you gain by using interface for even doing the SystemVerilog RTL, right? And second thing is, that's one thing from the module point of view, that you are declaring a named bundle of wires. And second is, when those have to be connected, they can just be implicitly connected as single wire as well, right? So instead of dealing with hundreds of discrete wires or variables, where you have a chance that when you're trying to manually connect, you can make a mistake, when you connect it as one single unit, there is very less chance that there is a mistake that can happen, right, when you're doing connecting a lot of modules, right? So when you're connecting fewer signals, as we are doing in our examples, it's not such a big deal. But in real designs, you know, there could be dozens of modules, and at least each of those modules could have thousands of interface signals, right? So on connecting all of them, it's differently a error prone process. And different companies in the past, before the SystemVerilog interface, have done automation to connect based on the names, their own internal proprietary automations. But this is the now standard language defined mechanism itself that solves that particular problem, right? And then if we have to create multiple instances of this particular like if the duty scales, instead of one port, it becomes like we had a single USB port, now we have 4 USB ports, then it's easy to create multiple instances of this particular interface instead of having to copy paste all the discrete set of signals, right? That's another advantage that you gain. And then the last one, which is very important from the verification point of view. So now this set of interface signals, which were more or less static, they were part of the static Verilog world, through the virtual interface now can be made accessible to the class-based dynamic test bench world, right? So what happens is, this is one subtle point, that when we declare an interface, it is static, but when we add virtual keyword to the same interface, when we are passing it around, now it becomes dynamic, right? And we can pass it to the class world, right? And then we will see how that can be further, we can utilize the virtual interface into the test bench as we go further in this session. So from the SystemVerilog language point of view, interface is almost equivalent to a module, right? What that means is, like, whatever the module can do, most of the things that even the interface can do, except for the fact that it cannot instance the modules or the program blocks itself. For example, a module can instance another module, or it can instance a program block. If we leave that out, the interface as a construct can hold almost everything that a module or a program block can hold, right? So you can put any functionality that you want within the interface. That doesn't mean you should stuff it, but it provides language, provides that capabilities. This is one thing that you have to always keep in mind, that SystemVerilog as a language can provide a lot of flexibility, but while using, you have to adhere to certain conventions that have been utilized as a best known practices, and we will discuss some of those as we look at every construct. We'll look at some of the best known practices, or if there are any gochas, we will talk about them as well. So it can have parameters. So I'm just expanding as to what exactly that means. It can have parameters, like the way modules have parameters. It can have parameters, constants, additional variables can be declared within the interface. Task functions can be defined, which can eventually drive and check the interface. Although personally, I have not seen any standard projects where they drive it using the interface, but it can be done. If you, as a support from a language point of view, it can be done. And your initial and always blocks can be defined for concurrent monitoring without interface is useful. Assertions can be added for protocol checking within the interface is also useful. And the functional coverage for the interface can be implemented within the interface construct, and is also useful, because once we do this, anytime you instance a interface, all of these checks and coverage automatically become available. So that's a benefit you gain. And because interface is similar to a module, whenever you instance an interface, it creates a hierarchy. What this means is, in the top TB, when I instance an interface, I can access it as top TB, that top TB with the dot notation, the name of interface, right? So that way I can access it. And once I am able to access that, the functionality that is present within the interface can be accessed with one more dot. So I can say, like, the top TB dot interface instance name dot, like, if I can now access any variable or access any function or access any property or a cover group, I can access anything that I have put in to the interface construct. Now let's just define a very simple interface, and we will look at how do we define it, how do we use it, and how do we connect it, right? Like, let's say I have now defined this interface construct is always defined with this interface keyword and the name of the interface and any inputs that I can pass to the specific interface. And then I will declare any wires that it is supposed to encapsulate, or like and the ones that are used for connecting the two entities of this interface type. All of them are defined, and generally in the SystemVerilog you use the logic data type to declare all your variables that are part of your interface. And then you say end interface, and you can give the same label. It's generally a good idea to follow this label, because if in a file there are multiple interfaces that are declared, and if there are more than a screen worth of information, then correlating this end of interface to the name becomes simpler. So this is how you declare an interface, and once you have declared it, what you can do is you can use them. So the way to use them is you can always say the name of like here for example module, and I am declaring a port of the type APB interface. So in a module I can declare a APB interface APB, and then this port can be driven by using the dot notation. So this is a way you can actually build the RTL. So you can say apb.p address equal to whatever the internal variables that you have, right? So you can access the name of the interface dot the signals or the variables that you have declared can be accessed. So that's how you use the interface. So note that we have not introduced still the concept of Modport over here. So here when this is the case, this particular module can drive the P address as well as it can read it back. There's no restriction over here. So now this bridge, although it is supposed to use this APB interface as a master, but it need not adhere to that, because now it is seeing them as wires. It can do anything. Either it can drive or monitor, both of the activities that it can do. So in the next one we will see how to assign the direction to it. But this is also from the language point of view, this is also a legal use case. So we can do like this. And then in the module top, what we are doing is we are instancing the modules. That is, let's say that this similar way I have built APB bridge and the APB slave. In the APB slave also I have passed the APB interface. So I have now here what I have done is I have created an instance of this particular APB interface, APB bus, and I have passed the respective inputs. And then now I have declared the two modules, APB bridge and APB slave. I have created an instance of them, and whatever this common the interface that I had declared, which is now sort of a wire equivalent, I am passing them to both of them, and this is it, right? So it can be connected like this. Now you can see how clean it is. Instead of, otherwise I had to do this, whatever 8 signals are there, I had to put 8 of the ports, and then I had to do that connection if in case of if we were doing the same thing in Verilog. Now it has become so simple. And if the same interface is being used in both of these modules, right, like this APB bridge and the APB slave, if they're using the same interface, you can also use this sort of implicit connection where they're using the dot star, and it will automatically connect both of them together. So this type of implicit connection is also possible over here, right? So both the two ways of connecting the interface is possible. So in the previous example, we were directly connecting the interface, but as we have discussed, we can also encapsulate the views, right? The essentially the port view of the interface as well. And here in this particular example, we are demonstrating the same, right? Without Modport, if we directly pass the interface, then we will not be able to restrict the access to these signals, right? So anybody could drive and anybody could monitor, but using the Modport, what you can do is you can restrict the access to interface resources and also enforce direction, right? Using the Modport you can do that. So if we, for the same APB example, if you look at it, when we create a Modport which is expected to be used by the bridge, then we can say master, and here you can see the input is slave error ready and the PR data, and whereas the output is P address and PW data P cell. Whereas when we look at the Modport for the slave, then it's reverse, right? So the output is P slave error, P ready and PR data, whereas P address and then the PW data and so on, they become input, right? So now this is the way we create the Modport. And Modport declaration within an interface adds another hierarchy. That is, whenever you access any of the resources, now if you are accessing it through the Modport, then Modport name also becomes a part of hierarchy. And in the previous example, when we were doing module APB bridge, we were directly passing the APB interface. Now if we want to restrict the access to this APB interface for the master in a specific way, then what we can do is we can say APB interface dot master, right? And then we can restrict the access. And this type of a concept is not limited to restricting access to the only wires, right? Like even the other resources that we create, like let's say we declare some tasks or functions, they can also be restricted through the Modport declaration. So we were looking at Modport. So what we can do is we can also generally the Modports are also combined with the clocking block, especially if you have a synchronous interface. So what we can this is the example that's demonstrating it. So we have a bus and we have declared this bunch of wires that are part of this bus. Now what we can do is we can declare a clocking block over here, and this clocking block is clocked by this passage of clock. And even within the clocking block, actually you can define the directions, and like here I'm defining input grant, output request address, and in-out data. And even within the clocking block I can define the properties. And then now what I can do is I can use this clocking block as a part of Modport, right? That is possible. So I am saying mod stb and clocking sb, right? And what happens is the clocking block itself adds another hierarchy again. So what will happen is you'll have interface name, and when we want to access any of the resources, now what we have to say is we have to say the interface name dot Modport name dot the clocking block name, right? And when you use the clocking block, of course all of these signals will be either sampled or driven on the clocking event with the default, the skews and the the output delay, the clock to output delay that we have specified. It becomes sampled and driven based on that. And when you use the clocking block as a part of the Modport, if you want to access something, these are some of the examples. So you can use it in your property with the name of the interface, the instance name of the interface dot the directly the clocking block itself can be accessed, and then I can access, like let's say, the property that I have declared within the clocking block. Or I could be accessing directly the signals that are defined within the clocking block. Or I can even, like for example, if I have declared this particular interface, this SIF, if it is of the type STB, it's a similar way. I can again use that instance name dot the clocking block name dot request equal to 1. And if it is of the type interface, then what happens is you can still access directly the clocking block. Or even if it is a type of the Modport, since this Modport has access to the clocking block, the hierarchical access remains similar. The notation is similar. It depends on from what hierarchy or the what type you are accessing, but the dot notation can be used either with the interface object or with the Modport object. And in both of these cases, the clocking block is accessible with a single dot away. Both of them can be accessed. And here you can see that we can actually declare multiple Modports, or as interface can contain multiple Modports, and we are using the clocking block as well. So in this one, this is the asynchronous one because we are not using any clocking block. So when you are driving the signals or sampling these signals, then doing it on a appropriate clock edge is the responsibility of the user. Whereas if you use it with a clocking block, then the clocking block takes care of it. And then we have declared another asynchronous interface for the test bench, wherein whatever the output from the DUT is now becoming the input, or input from the DUT is becoming the output from the test bench. So here now we will show the usage of methods within an interface. So we have an APB interface over here, and we have the Modports. So let's come to this Modports after a while. Let's first look at, we have now added two tasks over here. So we have added an APB write task that takes the input address and data, and using this data and address, it can now in the body of this particular task, it can follow the APB protocol and drive out the interface signals with the values that have been specified. Similarly, I can do APB read, and then it can provide, I am providing an input address, and the data read by this APB read can be provided out through this output argument of data. And then the tasks and functions defined within the interface. If I am using an interface object, then I can say interface object dot APB read or dot APB write, and I will be able to invoke the tasks or functions that I have declared within that particular interface. Or if I am using an object or the interface instance of a specific mod port, let's say from the master mod port, that is APB interface dot master, if I want to invoke, then what I have to ensure is that in that particular mod port I have to allow access to these tasks. So the way I do it is I will say import APB write and APB read. Now when I do this, even when I pass the interface instance through a mod port, within that again I can use that particular instance name, and still I'll be able to use the dot notation to call the APB write or APB read, right? But generally this type of driving type of a functionality is modeled as a separate driver. Even in our FIFO test bench we have seen through the class instead of directly putting it in the interface. But there are some special use cases where where they do it, which is for the overcoming some sort of limitations that exists. But the general usage, you really don't put the driver functionality directly into the interface. This is just shown that this type of capabilities exists as a construct. So in the previous slide, we saw that we could include tasks and functions along with the mod ports within the interface. So in this one, we can see that we can put properties, right? So I have put a property P cell valid at pause edge of clock, not is unknown of P cell. It checks that on every pause edge of the clock, the value of P cell should never become unknown, or the X, right? So it checks for that it remains always valid. And this property can be both, now here I am asserting as well as you can cover this particular property. Now so this is one example. So here what we can do is the like the functional aspect, that is putting tasks and functions in the interface. We said that it's not a good idea to use them for driving or like replacing the your driver and monitor functionality. But what you can do is here this is a very simple coverage and assertions, but sometimes the coverage and assertions may require building some extra auxiliary logic on which they rely in order to add the checks or add the functional coverage. That auxiliary code in the form of tasks or functions, or it could be always blocks, that part of the code can still be included as a part of interface. I think that is still a right use case. So what happens is in the design, right? So we have different performance requirements, or like the different they need to fit into the different environment use cases. And in order to do that, what happens is generally the module interface are parameterized, the number of address bits, data bits. So they all get parameterized, and the same concept can also be applied to interfaces. This works exactly similar to your module parameterizations. You say interface AXI interface, and then you use this pound, and then you can define a comma separated list of different parameters, and you can pass the initial value, so that if this parameter is not defined, then the initial value will be set to whatever the default value that we have specified. And after this list, you continue with your regular declaration of your input ports for the interface, then the bunch of wires that we are declaring. And while we are doing that, now what we can do is we can use these parameters, right? And then actually while declaring other variables, if they have to be some way through equation, if we need to derive the widths of this particular signal using the parameter values, even that can be done for the rest of the signal declaration. And then if you have any tasks or functions and you are passing any inputs, even for those you can use the parameter values. So this works almost similar to the way you would do it for a module. And while now instancing a parameterized interface, what you do is, so you say AXI interface, which is name of your interface, and then you say pound, and then through the dot you can specify the name of the parameter. Either you can do like a name based association or a position based association, both are possible. So you can specify the name of the parameter and then the value that you want to provide. So the default value over here is 16 and the default value that you are providing over here is 32-bit, and then you can declare the instance name for this particular interface. So this way you can parameterize your interfaces. So let's now see the virtual interface. So virtual interface is a bridge, as we have used it already in our FIFO test bench as well, is a bridge between your static world of the signals and wires to the dynamic world of the class. And then so in the class-based world, you can't directly refer to the actual signals or the actual interfaces, so you always access it through a virtual interface, and a virtual interface becomes like any other variable. It's no longer static, so it can be also passed to your tasks and functions. And then the another advantage is that the virtual interface is not always tied to a specific interface, right? So you could have multiple physical interfaces, and in the test bench top you could have multiple physical interfaces, whereas in your test bench in any of the classes you can dynamically send any of those actual physical interface through a virtual interface handle, right? So any of them can be sent. And then as you can see, like a class data type also has a default value of null, and same the virtual interface also has a default value of null. And if you try to access without initializing a virtual interface handle, it results in error. And virtual interface instancing follows the same syntax as a static interface, apart from the fact that you prefix it with virtual space, name of the interface, and the name of instance. And virtual interface signals, the signals that are present within the virtual interface, are again accessed with a similar the dot notation that we saw in the actual static interfaces. So virtual interfaces can also be declared as class properties. So here you have declared a class, and I am declaring a virtual interface, virtual prefix space, the name of interface and the name of the instance, right? So I am able to do that, and then I can get the virtual interface as a part of the argument for the class constructor from let's say now we instance this one in the environment. The environment can pass the handle to the interface to this particular class, and then it can be initialized inside the virtual handle that's present within the class. And then I can then refer any signals that are present within the virtual interface using the dot notation, the bus dot request equal to 1. I can drive it, or then I can wait on it. This accessing is very similar to the way we do it with the static interfaces. And the modports and the clocking blocks, if they are present within the interface, even accessing the same with the virtual interface is no different compared to static interface. So in essence, the virtual interface behaves exactly similar to a static interface, except for the fact that it becomes dynamic, and then it can be used in the class based world, and you can connect any interface to any interface, that it doesn't get decided at the time of elaboration when it is compiling. Instead, it dynamically during the runtime you could be making any interface connection to any other interface connection using the virtual interfaces. That is what is the key point over here. So I think this concludes the session on interfaces. The key point was that for the interface, we need to look at it from the point of view of the connection. Look at it as a starting point, is as a connection between two modules, and then we start from there, and then you also encapsulate the view of these particular connects from the two entities that are getting connected, who have the ports, right? And those ports restrict the way you access this set of signals that are connecting them, right? So that is handled in the interface construct using the mod port. And the synchronization information, if you want to add the timing for the synchronous interface, you can do it through the clocking blocks. And the clocking blocks also provide an ability to specify the direction which can be used in the mod port. And you have to remember that mod ports are not just for defining the direction, although predominantly they are used for defining the direction. The direction can be controlled for asynchronous type of an interface ports. You can control it through the mod port itself. Within the mod port you can define the direction, but using the clocking block also you can define the direction and use one of the clocking blocks in the mod port. So once you do this, the interface has encapsulated the ports on the two connecting entities plus the wires that are connecting them. And then what you can do is, once you have encapsulated it, you can put any additional things that you want to do with this communication. Like for example, you can drive it, although that's not recommended, but you can drive it still if you want. From the construct point of view, it is supported. You can put properties, you can put coverage, and then you can also put tasks and functions. And if you put tasks and functions within an interface, and if you want it to be accessible through a specific mod port is your view through which you are restricting access to the resources that are present within the interface. You can import those tasks or functions within the mod port and hence make them accessible through the mod port as well. And the interface can also be parameterized similar to your module. And the last important characteristics of interface is the virtual interface. So the only difference of the virtual interface is the regular interface without virtual keyword is static, that gets all connected during the point of elaboration, whereas your virtual interface you can dynamically keep changing even during the runtime. So in that it is very helpful in the class based test bench. So in all verification components you use the virtual interface. So only difference is use the virtual keyword prefix, and then rest of the access is either the access to the signals that are present or access to mod ports, access to clocking blocks, or any other resources works exactly similar to its static interface counterpart. And yeah, that concludes this session on interface. Thank you for listening.